the discovery of dark energy is accelerating the expansion. There's a whole section of the book on how it'll all end. And we do not know. We don't know.
The universe stretches out endlessly, a vast and mysterious place. We've only just begun to scratch the surface of its secrets, but amidst the wonders we've discovered lie some truly shocking theories. Phenomena so strange, they defy explanation. What the simulation could be, or the bizarre concept of black holes. What secrets of the cosmos are we still missing? 1. White holes. Black holes, with their insatiable gravity and point-of-no-return event horizons, are cosmic rock stars. But lurking in the realm of theoretical physics is their enigmatic counterpart, the white hole. Unlike black holes, white holes are theorized to be regions of space-time spewing forth matter and energy, a cosmic fountain in perpetual reverse. However, the existence of white holes remains firmly in the realm of speculation, shrouded in mystery and controversy. The very concept of a white hole arises from the mathematics of Einstein's theory of general relativity. Certain solutions to the equations predict the existence of these time-reversed singularities. However, these solutions come with a hefty caveat. They violate the fundamental laws of physics as we understand them. According to the second law of thermodynamics, the universe constantly strives towards increasing entropy, a measure of disorder. White holes, by spewing out organized matter and energy, seem to defy this principle. Furthermore, the immense gravitational pull of a white hole presents another seemingly insurmountable challenge. According to our current understanding, nothing, not even light, could escape its grasp. This creates a logical problem. If nothing can get out, how can anything come out in the first place? Despite these theoretical hurdles, some physicists have explored potential scenarios where white holes might exist. One intriguing idea involves them as the counterparts of black holes in a wormhole, a theoretical passage connecting two points in space-time. Matter falling into a black hole in one universe could, in theory, emerge from a white hole in another. However, this scenario raises even more questions about the nature of these exotic connections and the potential violation of causality. Another theory suggests white holes could be the remnants of a collapsed universe spewing out matter into a new one, like a cosmic Big Bang in reverse. However, this concept hinges on a far from complete understanding of the origins and nature of our universe. The mystery of white holes extends beyond their theoretical existence. Even if they do exist, their properties remain entirely speculative. What kind of matter or energy might they spew forth? How would they interact with their surroundings? These are questions with no definitive answers at present. The quest for white holes, then, is a journey into the unknown. They represent a fascinating paradox, a theoretical object defying known laws, yet potentially offering a glimpse into exotic realities beyond our current understanding. So do white holes exist as fantastical anomalies, or gateways to hidden universes? The answer, like the vast emptiness they might represent, remains tantalizingly out of reach. 2. Drake equation. Are we alone in the universe? This is the ambitious goal of the Drake equation, a formula developed by astrophysicist Frank Drake in 1961. It attempts to estimate the number of active communicative civilizations in our Milky Way galaxy. But within its elegant simplicity lies a vast landscape of uncertainty, making it a powerful tool for sparking scientific dialogue rather than delivering definitive answers. The Drake equation multiplies a series of factors, each representing a major hurdle in our cosmic search for life. The first, R*, signifies the rate of star formation in our galaxy. This number is relatively well-defined, thanks to astronomical observations. However, the equation then delves into the murkier territory of planetary system prevalence. The factor Fp represents the fraction of stars with planetary systems, and our understanding of this value has grown dramatically in recent years. The discovery of thousands of exoplanets suggests our solar system might not be as unique as once thought. But the equation doesn't stop there. The next factor, Ne, tackles the number of planets per star system that could potentially harbor life. This is where things get truly speculative. We still lack a definitive understanding of what constitutes a habitable zone, a region around a star where liquid water, a key ingredient for life as we know it, could exist. Additionally, the equation considers the fraction of planets with suitable environments that actually develop life, the likelihood of that life evolving into intelligent life, and the fraction of intelligent life that develops a technology capable of interstellar communication. These latter factors represent the greatest mysteries in the Drake equation. We have no concrete evidence for life beyond Earth, let alone the existence of civilizations capable of sending messages across the vast cosmic distances. The final term in the equation, L, represents the average lifetime of a communicative civilization. Are technological societies fleeting sparks, doomed to self-destruction within a few millennia? Or can they persist for millions, even billions of years? So what can we glean from the Drake equation? Despite its uncertainties, it serves as a valuable framework for considering the vastness of space and the potential for life elsewhere. Each factor represents a scientific endeavor, pushing the boundaries of our knowledge in fields like astronomy, astrobiology, and even evolutionary biology. 3. Fermi paradox. The universe stretches out for billions of light years. With such vastness, the odds seem overwhelmingly stacked in favor of life arising elsewhere. Yet, amidst this cosmic abundance, we find ourselves facing a profound and unsettling silence. This is the crux of the Fermi paradox, a thought experiment that challenges our assumptions about the prevalence of extraterrestrial intelligence. The paradox takes its name from physicist Enrico Fermi. During a casual lunch conversation in 1950, the discussion turned to the possibility of extraterrestrial civilizations. Fermi, contemplating the vast age of the galaxy and the potential for interstellar travel, famously remarked, "Where is everybody?" The crux of the paradox lies in the tension between two seemingly contradictory ideas. On one hand, the universe is incredibly vast and old. Billions of stars have existed for billions of years, providing ample time and opportunity for life to emerge elsewhere. Additionally, some theories suggest interstellar travel might be achievable, allowing advanced civilizations to explore and colonize the galaxy. Given these factors, the Fermi paradox suggests we should see some evidence of extraterrestrial intelligence by now. We might encounter alien probes, receive radio signals from distant civilizations, or even find remnants of their activities on planets orbiting distant stars. Yet despite decades of searching through vast swaths of the electromagnetic spectrum and scrutinizing exoplanets for signs of life, we've come up empty-handed. So, where is the disconnect? Perhaps our assumptions about the ease of interstellar travel are flawed. Maybe the distances involved are simply too vast, making galactic colonization an insurmountable challenge. Alternatively, the development of advanced intelligence might be a rare occurrence, a cosmic fluke that has only happened here on Earth. Another possibility, often referred to as the Great Filter, suggests there's a critical stage in the evolution of life that acts as a bottleneck, preventing most civilizations from reaching technological advancement. This filter could be anything from a devastating asteroid impact to the inherent difficulty of developing complex social structures. The Fermi paradox doesn't offer solutions, but rather serves as a springboard for scientific exploration and philosophical contemplation. It forces us to reevaluate our place in the universe and consider the possibility that we may be alone, a lonely speck of intelligence amidst a vast cosmic ocean. 4. Earth-like Venus theory. Venus, our closest planetary neighbor, is a world covered in a thick, scorching atmosphere. Its surface temperature rivals that of molten lead, making it the hottest planet in our solar system. This infernal landscape stands in stark contrast to Earth, with its temperate climate and abundant life. Yet, a theory persists, suggesting Venus may not always have been the hellish world it is today. Could Earth's seemingly benign twin have once been a verdant paradise, harboring liquid oceans and perhaps even life? The seeds of this theory lie in the similarities between the two planets. Venus is roughly the same size and density as Earth, suggesting a similar formation process. Additionally, recent studies have revealed evidence of past plate tectonics on Venus, a geological phenomenon crucial for regulating Earth's climate. This suggests Venus might have possessed a cooler, more Earth-like environment in its distant past. The culprit behind Venus's transformation, according to the theory, is a runaway greenhouse effect. The current Venusian atmosphere is dominated by carbon dioxide, a potent greenhouse gas that traps heat from the sun. A runaway effect could have occurred when a series of volcanic eruptions or a massive asteroid impact spewed vast quantities of this gas into the atmosphere. This trapped heat would have triggered a domino effect, melting polar ice caps and releasing even more carbon dioxide locked away in the rock formations. The result would be a relentless cycle of rising temperatures, culminating in the scorching inferno we see today. But the mystery deepens when we consider the fate of any potential Venusian oceans. The runaway greenhouse effect would have boiled them away, leaving behind a barren wasteland. However, some scientists propose the possibility of hidden reservoirs of water trapped deep underground. Missions to Venus aim to investigate these possibilities, searching for signs of past water and potential clues about the planet's dramatic transformation. The Earth-like Venus theory holds profound implications. It suggests that even seemingly stable planets can undergo catastrophic environmental shifts. This raises a critical question. Could Earth suffer a similar fate? 5. Simulation theory. Imagine a world meticulously crafted not by the hand of nature, but by the processing power of a supercomputer. This is the intriguing proposition of simulation theory, a concept that challenges our very perception of reality. It posits that what we experience as the universe, with all its complexity and wonder, could be nothing more than an elaborate simulation, a digital construct created by an advanced civilization far beyond our comprehension. The seeds of this theory were sown by philosophers like René Descartes, who pondered the nature of reality and the possibility of deception by our senses. However, it gained new life in the field of computer science with the rise of powerful computers and increasingly sophisticated virtual worlds. As technology progresses, the line between simulation and reality blurs. Games like Second Life offer a glimpse into a future where virtual worlds become indistinguishable from the physical one. Proponents of simulation theory argue that if technological advancements continue at their current pace, civilizations in the distant future might be able to create incredibly realistic simulations. These simulations could be populated with conscious beings unaware of their simulated nature. According to this theory, it's statistically more likely that we ourselves are living in such a simulation rather than being the original reality. The mystery deepens when we consider the implications of such a scenario. If our reality is a simulation, who are the programmers? What are their motivations for creating it? Are we mere characters in a cosmic game, or do we possess some degree of free will within the confines of the simulation? Furthermore, the theory raises profound questions about the nature of consciousness and existence. If our reality is simulated, does it diminish the significance of our experiences? Or can consciousness and free will still exist within a simulated framework? Simulation theory, by its very nature, remains outside the realm of scientific testing. We have no way to definitively prove or disprove whether we are living in a simulation. However, the theory continues to spark philosophical debate and scientific exploration. It pushes us to consider the boundaries of what we know and compels us to reevaluate the nature of reality itself. 6. Black holes. Black holes are cosmic enigmas, regions in space-time where gravity reigns supreme. Their pull is so immense that not even light, the fastest entity in the universe, can escape their grasp. This very characteristic, the inability to directly observe them, shrouds black holes in mystery, making them some of the most fascinating and perplexing objects in the cosmos. Our understanding of black holes stems from the theory of general relativity, Einstein's revolutionary theory of gravity. It predicts that when a massive star collapses under its own weight, its immense density can warp spacetime to such a degree that a one-way point of no return is created, the event horizon. Beyond this boundary, the pull of gravity becomes so strong that nothing, not even information, can ever escape. But black holes aren't simply cosmic vacuum cleaners. They are shrouded in a swirling disk of superheated gas and dust called an accretion disk. This material, drawn in by the black hole's immense gravity, spirals inward at incredible speeds, reaching temperatures that cause it to emit intense radiation across the electromagnetic spectrum. This radiation, from X-rays to radio waves, allows us to indirectly detect the presence of black holes, even though we cannot observe them directly. Black holes come in a variety of sizes. Stellar mass black holes, formed from the collapse of massive stars, can be several times the mass of our Sun, crammed into a region no larger than a city. At the other end of the spectrum lies supermassive black holes, residing at the heart of most galaxies, including our own Milky Way. These behemoths can be millions or even billions of times more massive than the Sun. The mystery of black holes deepens when we consider their potential impact on their surroundings. Recent observations suggest supermassive black holes can unleash powerful jets of particles traveling close to the speed of light. These jets can stretch for vast distances, potentially influencing the formation of stars and galaxies. But perhaps the most intriguing aspect of black holes lies in the realm of theoretical physics. Some theories propose the existence of a singularity, a point of infinite density at the center of a black hole, where the laws of physics as we know them break down. Additionally, the concept of Hawking radiation, theorized by Stephen Hawking, suggests that black holes might slowly evaporate over vast stretches of time. So what secrets do black holes hold? Are they simply cosmic dead ends? Or could they be gateways to another dimension, a portal to a reality beyond our current comprehension? 7. Big Rip. Our universe is constantly expanding, stretching the fabric of space-time ever outwards. But what if this expansion isn't a gradual stretching, but a relentless acceleration leading to a catastrophic end? This is the unsettling proposition of the Big Rip theory, a scenario where the very essence of space itself is ripped apart in a final, violent tear. The culprit behind the Big Rip is a mysterious entity known as dark energy. Unlike normal matter, which exerts a gravitational pull, dark energy possesses a repulsive force, pushing everything in the universe further apart. While the exact nature of dark energy remains unknown, its existence is inferred from observations of the universe's accelerating expansion. The Big Rip hinges on a specific property of dark energy, its equation of state. This equation relates dark energy's pressure to its density. If dark energy's pressure becomes increasingly negative as the universe expands, its repulsive force overpowers gravity at an ever-increasing rate. This runaway expansion would ultimately tear apart the universe at its most fundamental level. The first casualty in this cosmic tug-of-war would be large structures like galaxies. The immense distances between galaxies would stretch beyond the reach of their gravitational pull, causing them to break apart. As the expansion accelerates, even smaller structures, like star clusters and solar systems, would succumb to the relentless rip. Eventually, the bonds holding atoms together, the very building blocks of matter, wouldn't be strong enough to withstand the cosmic pull. The mystery of the Big Rip lies in the uncertainty surrounding dark energy. We don't know its exact nature or its equation of state. If dark energy's repulsive force remains constant or even weakens over time, the Big Rip wouldn't occur. The universe might continue to expand forever, reaching a state of perpetual coldness and darkness known as the heat death. However, if the Big Rip scenario is even remotely plausible, it raises profound questions about the ultimate fate of the cosmos. Would time itself come to an end as the fabric of space-time tears apart? Or could the Big Rip represent a transition to a completely different kind of universe, one beyond our current comprehension? The vastness of time allows for some comfort. Even if the Big Rip is inevitable, it's likely billions of years away. 8. Time is running out. The vast expanse of the universe stretches out before us, seemingly infinite in its scope. Yet, a disconcerting theory whispers of a looming deadline, a point in time where the very fabric of reality becomes unstable. This is the idea of the time is running out theory, a collection of ideas suggesting the universe might have a specific expiration date. One such theory hinges on the nature of dark energy, the mysterious force driving the universe's accelerated expansion. Some interpretations of dark energy suggest it might not be a constant force, but rather a slowly evolving entity. If dark energy's properties change over time, it could hypothetically morph into a destructive form, ripping apart the universe in a scenario eerily similar to the Big Rip. However, the time is running out theory extends beyond dark energy. Another unsettling possibility concerns the potential instability of the vacuum itself. The laws of physics, as we understand them, predict a baseline energy level, even in the absence of matter or radiation. This vacuum energy might seem harmless, but some theoretical models suggest it could hold immense, hidden potential. If this vacuum energy were to suddenly and unexpectedly change state, it could release a catastrophic burst of energy, tearing apart the universe in an instant. The mystery deepens when we consider the concept of the multiverse, the theoretical existence of an infinite number of universes. Some versions of multiverse theory suggest universes can decay or transition into different states. If our universe is nearing such a transition point, it could signify the end of everything as we know it. The problem with these time is running out theories lies in their inherent speculation. They rely on hypothetical scenarios and exotic physics concepts that remain outside the realm of confirmed observation. We simply don't have enough information about dark energy, the true nature of the vacuum, or the existence of a multiverse to definitively assess these threats. However, the theories serve an important purpose. They push us to refine our understanding of the fundamental laws that govern the universe. By exploring these unsettling possibilities, we delve deeper into the nature of reality and the potential dangers that might lurk within the vast expanse of space and time. So, is our universe hurtling towards a predetermined end? Or are these theories simply products of our limited understanding? 9. Heat death. Think of the universe as devoid of vibrant stars, a cosmic wasteland where all energy has reached a stagnant equilibrium. This is the chilling prospect of the heat death theory, a scenario suggesting the ultimate fate of our universe is not a fiery bang, but a slow, relentless descent into an inescapable cold. The theory stems from the second law of thermodynamics, a fundamental principle governing the flow of energy in closed systems. This law states that entropy, a measure of disorder, always increases over time. In simpler terms, usable energy has a natural tendency to degrade and spread out, becoming less concentrated and therefore less useful for any kind of work. Applied to the vast cosmic stage, the heat death theory suggests that all the stars in the universe will eventually exhaust their fuel and burn out. As stars die, they can no longer generate the heat and light that power the celestial machinery. Black holes, the ultimate consumers of matter, might gobble up any remaining stellar remnants, further concentrating, but ultimately isolating usable energy. The universe, once filled with burning stars, would then be left with dwindling pockets of hot, isolated objects like black holes, surrounded by a vast, ever-expanding expanse of cold, inert space. In this state, no new stars could form, and any remaining pockets of heat would slowly dissipate, radiating away into the ever-chilling cosmic background. The mystery of the heat death theory lies in its timescales. The universe is vast and old, and the process of stellar burnout unfolds over billions of years. While the eventual heat death seems inevitable, the timescales involved are so immense that they become almost unfathomable from a human perspective. However, the heat death theory doesn't paint the whole picture. Recent discoveries of dark energy, a mysterious force driving the universe's accelerated expansion, complicate the equation. Depending on the properties of dark energy, It's possible the universe might expand so rapidly that structures like galaxies wouldn't even have time to form, let alone stars. This scenario, known as the Big Rip, presents an alternative, a universe torn apart by its own expansion rather than succumbing to a slow, cold demise. The heat death theory serves as a stark reminder of the impermanence of all things, even on a cosmic scale. It compels us to contemplate the vastness of time and the ultimate fate of our universe. But it's important to remember that the heat death scenario is just one possibility. Do you think this theory could actually be possible? 10. The first signal. Carl Sagan, a renowned astronomer and champion of scientific exploration, explored the profound implications of encountering extraterrestrial intelligence in his thought-provoking novel, Contact. Within its pages, he presented a chilling possibility. What if the first impression we make on alien civilizations isn't a beacon of hope, but a horrifying echo of humanity's darkest hour? The theory hinges on a historical fact: the immense power of the 1936 Berlin Olympics radio broadcast. This event, marred by the rising tide of Nazism, featured an opening speech by Adolf Hitler. The sheer technological advancement of the German radio transmission at the time meant it had the potential to pierce Earth's ionosphere and leak out into the cosmos. Sagan, ever the visionary, recognized the unsettling implication. If alien civilizations were actively searching for signals from Earth, this potent broadcast, carrying the voice of a dictator, could be the first they encounter. Imagine the shock, the confusion, or even the fear an alien civilization might experience upon receiving such a message. Would they see this as a representation of humanity as a whole? The mystery deepens when we consider the vastness of space and the timescales involved. Radio waves travel at the speed of light, meaning a message from 1936 could still be traversing the cosmos, potentially reaching alien ears millennia later. Thankfully, advancements in communication technology have allowed us to send more diverse messages. Projects like the Voyager Golden Record, a spacecraft-borne record containing greetings, sounds, and images from Earth, offer a more holistic view of humanity. However, the Hitler First Contact scenario serves as a powerful reminder. It shows us the importance of crafting well-considered interstellar communication, messages that transcend singular events and showcase the full spectrum of human experience. We are not defined solely by our darkest moments, but by the sum of our achievements, our struggles, and our capacity for compassion. Do you think aliens have already intercepted the chilling echoes of the 1936 Olympics broadcast? And is this something we should be worried about? Now that we've discussed all these theories, let us know which one you think is most likely to be true. Let's get the conversation going in the comments section below. If you loved the video, give it a huge thumbs up and subscribe to the channel if you want more content just like this. As always, thanks for tuning in. See you in the next one.